So what's going on, everybody? We got a nice little video here. Gonna be a pretty long one. It's curve sketching. So this is the one where we graph the rational functions, and we've got some logarithmic functions and some trig functions and all that good stuff. And here's the problems I'm gonna be working. And actually I think I'm gonna throw one more in there, problem number 7, where we work a graph that has a hole in it. So there'll probably be one more. All right, so here's some guidelines for curve sketching. First thing you want to do is find the domain. Okay, find the domain of your function, then find any x and y intercepts. Look and see if it's symmetric. Remember, you learned this back, if you took pre-calculus, you learned about odd and even functions. Remember, if you evaluate the function at negative x and you get the original function back, then it's an even function. That means it's symmetric about the y-axis. And then if you got f of negative x is equal to negative f of x, then it's an odd function that would be symmetric about the origin. And then periodic functions. That means when you graph something and you graph it over a certain interval and then it repeats. Okay, examples: sine, cosine, tangent, your trig functions, those are periodic functions. Asymptotes, we want to find horizontal, vertical, and slant asymptotes. Slant asymptotes or oblique asymptotes. We have one where we do a slant asymptote. And then we want to find intervals where the function's increasing and decreasing, any local maximum or minimum values. We want to see where it's concave up, concave down, and find any inflection points. And then we'll use all this information here to sketch the graph. So let's go ahead and get started. So here's the first problem. Number 1, I'm going to rewrite the problem down here. All right, so we got number 1. That's going to be y is equal to 2x squared over x squared minus 1. All right, so first thing we want to do, we want to look and find the domain of the function. So for the domain, all right, so remember we got a fraction here, so the domain is going to be, for this one, it's going to be everywhere except where the denominator would be 0. And so, I know you probably don't have to do this, but if you set it equal to 0 and solve, you would get x equals plus or minus 1. So x cannot be plus or minus 1. That would make the denominator undefined. So our domain is everywhere except plus or minus 1. So the domain would be negative infinity to negative 1, or negative 1 to 1, or 1 to infinity. All right, so there's your domain. And I'm just going to go ahead and circle this. Might make it a little easier for us to go back and pick all this stuff out when we're graphing the functions. All right, so now let's look at intercepts. All right, so let's look at the x-intercept. So for the x-intercept, remember how to find that? That's where you set the function equal to 0 and solve. So just remember, y is equal to 0 when, in other words, the function y is equal to 0. This function here, y, is equal to 0 when 2x squared equals 0. Remember, a fraction is 0 when the denominator is 0. And so this gives us x is equal to 0 when we solve it. And so our x-intercept is 0, 0. And of course, I know you realize this, the y-intercept, it's the same thing, but I'm going to go ahead and work it out just so you can see it. So remember, to find the y-intercept, you plug 0 in for x, And of course, that will give us 0. So, I mean, of course, this is 0, 0. You don't have to write it twice, but they're not going to be the same every time. So, all right. All right, so there's your domain, your intercepts. Now, let's go ahead and look for symmetry. All right, so for symmetry, and I'm gonna, as we go down, because you know I'm gonna run out of room as we go down, so I'm gonna go ahead and just write the function down here so we can see it. All right, so for symmetry, well, remember symmetry, we take the function and we evaluate it at negative x. And so when I take the negative x here and I plug it in our function here, that's going to give me 2 times negative x squared over negative x squared minus 1, which that's 2x squared over x squared minus 1. And you can see here, I get the original function back. So that's actually equal to y of x. So that tells me this is an even function. All right. So that means it's symmetrical about the y-axis. So really all I need to do is just graph half of it, and then I can mirror the other half over. All right, so now let's look at the asymptotes now. So we've got our asymptotes. And I'm going to just grab this and bring it down so we can see the function. All right, so we've got to look for horizontal and vertical asymptotes. So to do that, hopefully you remember how to do this. You learned this earlier in calculus when you did limits. So let's look at the vertical asymptotes first. So we've got the vertical. All right, so you find the values where the function is undefined. And in this case, we know it's plus or minus 1. And then we want to take the limit of this function as x approaches 1 from the left or the right. And if that equals infinity or negative infinity, then that means there's a vertical asymptote there. And then we'll do the same thing with negative 1. All right, so let's do the limit as x approaches negative 1 from the left. All right, of 2x squared over x squared minus 1. Now, so if I'm coming in to negative 1 from the left, so don't get confused here. If you need to, just mark them on the number line, and we're coming in from this side. So this is negative 2. All right. So we're going to be plugging in numbers like negative 1.001. Okay. And then I'm going to square it. Of course, that's going to give me a positive. So the numerator is going to be right around 2. And the denominator, well, if I take negative 1.0001 and I square it, it's a little bit more than 1. So this is going to be positive down here, but it's going to be a really small number. It's going to be like 0.00001. But the numerator is staying right around 2. So that tells me this is going to infinity. All right. Now, that right there, to show that negative 1 is a vertical asymptote, that's all we have to do. That's it. You've just got to show that if it's coming in from the left, that it equals infinity or negative infinity. Or we could have come in from the right and shown that that equals plus or minus infinity. But what I'm going to do is I'm going to do the limit as x goes to negative 1 from the right of 2x squared over x squared minus 1. Now, I don't have to show this to show that there is a vertical asymptote at negative 1. The reason I'm doing this, okay, the reason you want to do this when you find those values where it's undefined, okay, you want to take the limit coming in from the left and from the right, okay? And the reason is so that we can see how to draw the graph, okay? It tells us how to draw the graph when we're coming into -1 from the left and when we're coming in to -1 from the right, all right? And so this one, see if I'm coming in from the right here, that's numbers like -0.9999. So you can see this is going to still be around 2 on the numerator. The denominator, that's going to be like -0.00001. So this one is going to -infinity. And then we will do the same thing, okay? We'll do the same thing. The limit as x approaches 1 from the left of 2x squared over x squared minus 1. And we'll do the limit as x approaches 1 from the right of 2x squared over x squared minus 1. Now, once again, if you need to, just draw your number line. So we're coming in from the left, so we're plugging in numbers like 0.999. So you can see this is going to go to -infinity, and then if we come in from the right, we'll be plugging in numbers like 1.0001. So we can see that's going to infinity. So we do have vertical asymptotes at x equal -1 and x equal +1. All right. So there's the vertical asymptotes. Now let's look at the horizontal asymptotes. So let's pull this down so we'll have it down here with us. All right. So now for the horizontal asymptotes, I want to take the limit as x goes to infinity of 2x squared over x squared minus 1. All right. So to take the limit as of a rational function as x goes to infinity or -infinity, we're going to write it the limit as x goes to infinity of 2x squared over x squared. You just keep the largest exponent from the numerator, largest exponent from the denominator. You learned this back when you did limits. If you need more on this, just search my channel, limits at infinity for rational functions, and I've got a video going over all that. And so this is the limit as x goes to infinity, and the x squareds cancel out, and so that's 2. So I do have a horizontal asymptote at y equal 2. But now also I want to take the limit as x goes to -infinity. Obviously it's going to be the same thing, but we're still going to go through the process of showing all the work and everything. So this is, and the reason we want to do this is because, well, we need to know how to draw the graph when it's going to -infinity. Okay, that's why we're finding all this. So this is the limit as x goes to -infinity of 2x squared over x squared, which equals the limit as x goes to -infinity of 2, because once again the x squareds cancel out, and so I get 2. So I have a horizontal asymptote at y equal 2. All right, so there's your domain, okay? Domain, intercepts, symmetry, asymptotes. All right. Now we've got to do the increasing, decreasing, local max, min, concavity, inflection points. So you would have most calculus books. There's another section before this one where it goes over graphing, and it's more like polynomials and stuff. And when you're graphing the polynomials and stuff, remember you're finding your critical numbers, then increasing, decreasing, local max, min, concavity, inflection points. Well, that's what we're doing now. Okay, we're doing it with these rational functions, which you probably know already, but if not, you'll see they get a lot messier taking the derivatives. All right, so now let's do increasing. No, let's do that in a different color. So increasing, decreasing. All right, so we've got y equals 2x squared over x squared minus 1, and we have to take the derivative of this thing. All right, so we get y prime is equal to, so remember we got quotient rule here, so that's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, and that's all over the denominator squared. All right. So let's see what we get. That is going to be 4x cubed minus 4x minus 4x cubed all over x squared minus 1 squared. And so we get y prime is negative, and that's going to be 4x over x squared minus 1 squared. See this, the 4x cubes go out, so I'm left with the negative 4x. I just took this negative and put it outside here. All right, so we're finding our critical numbers now. So we've got to set y prime equal to 0. Well, we know y prime is equal to 0 when the numerator is equal to 0, and so that's when x equal 0. All right. So now we need to plot this on a number line. So I've got 0. Now, remember your critical numbers, that's where the first derivative is 0 or where the first derivative is undefined. That's your critical numbers, provided that those numbers are in the domain of the original function. Well, the first derivative is undefined at plus or minus 1, okay? But so is the original function. So plus or minus 1 are not critical numbers, okay? However, we want to take those numbers and plot them on the number line, because this thing could change increasing, decreasing. Sometimes it may not, okay? But you want to put, when you're doing your number line, you want to plot on that number line where the first derivative is 0 and where it's undefined. But keep in mind, in this problem, 0 is a critical number, but -1 and +1 are not. Okay? And so now we're gonna pick numbers from each interval. All right. And so then we're going to have to do y prime of -2. All right, so I'm going to take this, and I'm going to take the -2, and I'm going to plug it into this one. Okay, this one right here. So just keep in mind the denominator here is always positive. See, I don't care what the exact value is. I just want to know, is it positive or negative? Okay, so no matter what I plug into the denominator, that's going to always be positive. So when I plug the -2 into the numerator, that's going to be a negative up here, but the negative and negative make a positive, and the denominator's positive. So this is positive, so it's increasing. All right, and then I got y prime of -1/2. So that's going to be positive down here, negative, negative, that's positive. And so that's increasing. And then y prime of 1/2, well, that's positive in the denominator, positive in the numerator, but then we've got the negative here, so that's less than 0, so that's decreasing. And then I've got y prime of 2, so that's positive in the denominator, positive in the numerator, but the negative out here makes it negative. That's less than 0, so it's decreasing. And so we have this thing decreasing from 0 to 1 and from 1 to infinity. And go ahead and split these intervals up, because you don't really want to say 0 to infinity, because the function's undefined at 1. And then we've got increasing from negative infinity to -1 and -1 to 0. So there's your increasing and decreasing. All right, so now we've got local max min. All right, so now local max min values. So remember, that's where it changes from increasing to decreasing or decreasing to increasing. And we can see up here in this problem that see how it's changing here. There's your local maximum. Okay, there's no local minimum because it doesn't change anywhere else. It just changes here, and that's your maximum. So we have a local maximum at 0. So there's a local maximum at 0, and now we need the y value. Now, this is where you want to be careful. Okay, we've got the 0. Okay, how do I get my y value? 0 is my x value. How do I get my y value? To get the y value, you evaluate the original function at 0, which of course we know that's 0 already. And there's your local max min. All right. All right, so now concavity. So for concavity, well, or concavity and inflection points, so yeah, I've got to take the second derivative, and this ought to be fun, huh? Well, first let's just go ahead and write down the first derivative. That's negative, and that's 4x over x squared minus 1 squared. So I need to find the second derivative. I'm going to go ahead and put my negative there. And then let's see what we've got. So remember, it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. All right, so the derivative of the numerator times the denominator minus the derivative of the denominator, so the 2 comes down, chain rule here, right? Subtract 1 from the exponent, so that's just going to be an exponent of 1 times the derivative of what's inside the parentheses times the numerator. And this is all over the denominator squared. All right. So here we go. Do you see right here the common factor x squared minus 1? I'm going to factor that out. So I've got y double prime. There's my negative. So I've got x squared minus 1. Right. Times, and that's going to be 4 times x squared minus 1 minus, and that's going to be 16x, and that's over x squared minus 1 to the 4th. We got the 2 times 2. All right, so I factor out the common factor of x squared minus 1, and so that takes that to an exponent of 1. There's that. And then when I take it out of this, I'm just left with the 2 times 2, and this should actually be x squared there. All right, so I've got 2 times 2 is 4, or 2 times 2x is 4x, and 4x times 4x is 4x squared. I mean 16x squared. And so, and then I've got the minus in front. All right. And so now we've got, now look at this. See, x squared minus 1, x squared minus 1, that's left with a cubed. And so I'm left with 4x squared minus 4 minus 16x squared over x squared minus 1 cubed. And so, and let me bring my negative down. And so this is going to be negative 12x squared minus 4 over x squared minus 1 cubed. And so this will give us, let's see, oh, and don't forget the negative. And so this will give us y double prime is equal to, well, let's factor out that negative. So that's going to be a negative, and that's going to be negative 12x squared plus 4 over x squared minus 1 cubed. And so I get y double prime is equal to the negative and negative, make a positive. So that's going to be 12x squared plus 4 over x squared minus 1 cubed. Now, notice here we've got y double prime will never equal 0. Okay, it will never equal 0. Why? Well, you probably can see it, but let me just show you. So if you take this thing and you set it equal to 0, okay, then you're going to get x squared is equal to negative 1/3. And so you get x is equal to plus or minus I square root of 1/3. And of course, you know, you can simplify square root of 1/3. But what I'm getting at is notice when you solve this thing, you get this an imaginary solution. So that numerator will never be 0. Okay, it'll never be 0. All right, but that's what you do. You set the second derivative equal to 0, and whatever you get for x, that's what you plot on the number line. But in this case, the numerator will never be 0. So what do? Well, just like before, it's undefined at plus or minus 1, right? Second derivative is undefined at plus or minus 1. So we're going to plot those on the number line just like when we did the increasing and decreasing. And so I've got x equal negative 2, x equals 0, and x equal 2. And so now we got y double prime of negative 2. So if I take the negative 2 and I plug it into here, okay, the numerator is going to always be positive. But the denominator, let's see, that's going to be 4 minus 1, that's positive. So this is greater than 0, so this is concave up. And then I've got y double prime of 0, well, that's positive in the numerator. Oh, but the denominator will be negative, so that's going to make the whole thing less than 0, so that's concave down. And then I've got y double prime of 2, well, that's going to be positive also, so that's concave up. So we have concave down from negative 1 to 1, and concave up from negative infinity to negative 1, and from 1 to infinity. All right, now we've got inflection points. All right, so inflection points, remember, that's where the graph changes concavity. Okay, well, it changes concavity at negative 1 and 1. So does that mean there's inflection points there? Well, no. And why not? Well, because the function's undefined at negative 1 and 1, right? I mean, you can try it. Go plug negative 1 and 1 back into the original function, and you'll see you'll get 0 in the denominator. Okay, so there's no inflection point, so that would be none. All right, so here's my concavity, and here's my inflection points. Well, now we're ready to draw the graph. All right, so to draw the graph, we got to take all that information that we found and use it to sketch the graph. So I'm going to pause the video, and I'm going to write all that information right here so we have it all in one spot. All right, so I've got all the information just jotted down right here, so I wouldn't have to keep scrolling up and down to draw the graph. So let's go ahead and draw this graph. So what I want to do, I just want to come in here and just mark off all these important points. So let's see, let's just do this. Let's go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right, so let's mark off -1, and there's 1, and there's y equal 2, okay? And the reason I did that, well, remember we got our vertical asymptotes at -1 and 1, okay? We got a horizontal asymptote at 2. All right. We've got a local maximum at 0, 0. And so we've got all the points and asymptotes and all that good stuff. We've got all that drawn in. So now it's just a matter of reading the increasing, decreasing, and all that good stuff. So let's see what happens. When I come in, I'm just going to go from left to right. So as I come in to -1 from the left, so that's where these limits come in handy. So as I go into -1 from the left, where's that thing going? To infinity. It's going up this way. And then remember, as I go to -infinity, the graph is approaching 2. Remember, that's my horizontal asymptote. I didn't write those limits down, but remember we also had that limit as x goes to -infinity. Then it went to 2, and the limit as x went to +infinity, it went to 2 also. So it looks like that graph, so when I come here, it's going to infinity, and as I go this way, it's approaching the line y equal 2. So that graph is going to look like this. All right, so now we've got this side of the asymptote. Now let's jump into here and see what that looks like. So what's happening is I'm coming into -2 from the left-hand side. Oh, and then also we can look at the increase, and we can double check all this to make sure we drew this right. All right, I just kind of looked at the limits here to see, what it was doing. But look at this. We can see that from -infinity to -1, -infinity to -1, it's increasing, and that's what we've got. And then also from -infinity to -1, it's concave up. So I can see that I drew it right. That's one thing that you could try, is just kind of sketch it in there, just draw it in like you think, and then go back and verify this on what you've got is, how increasing, concavity, and all that stuff to make sure you did draw it right. So now as we come into -1 from the right-hand side, well, let's see, what is that going to do? There's -1 from the right. That's going to -infinity. You see that? And then we can also see that from, where is it? From -1 to 0, it is increasing, so I know it's coming that way. And from -1 to 1, it is concave down. So I know that the graph right here is going to look like, that's not a very good drawing, is it? All right, so I know it's going to look something like that, okay? And now look, this right here is where you can just stop, because we know that it's an even function. So it's symmetrical about the y-axis, so I can just mirror this over here, which that would come in here like this, and I could mirror this over to this side, it would come in like this. Okay, so that's the option you have, is to mirror it over. All right, and that's fine, and I just showed you how to do it, but let's keep going through it, reading our limits and increasing, decreasing, and all that good stuff. So as we come into 1, this is the line x equal 1. As we come into 1 from the from the left-hand side, so we come into 1 from the left-hand side, see how it's going to -infinity? And look at this, from 0 to 1, it's decreasing. So that means it's going to come in here like this. And you can see -1 to 1, we're concave down. All right. Then, as we come into 1 from the right-hand side, so coming into 1 from the right-hand side, that's going to infinity. So That's going to come in there like that. And as x goes to infinity, it's approaching 2. And so we'll draw that in like that. And once again, you can verify from 1 to infinity. See right here, it's decreasing. And from 1 to infinity, it's concave up. And so there's your graph. All right. And you can see we're already about 30-something minutes into the video. And that's the first problem. This is going to be this real long video. All right, so let's go ahead and jump on to example 2. All right, so let's take a look at this problem. We've got y equals x squared over the square root of x plus 1. We want to graph it. So we're going to find the domain, intercept, symmetry, asymptotes, increasing, decreasing, local max, min, concavity, inflection points. All right, so first thing, let's find the domain. So for the domain, well, let's look at it. We know we can't have 0 in the denominator, and we know that -1 makes the denominator 0. But we also have a square root, and we know we can't take the square root of a negative number. So what's underneath the square root, the x plus 1, has to be positive, right? It can't be negative. And we're not going to be able to put the or equal to because we can't equal 0. So it's just going to be where is x plus 1 larger than 0? And we can see that is when x is greater than -1. So our domain would be -1 to infinity. All right. And let's go ahead and circle this because we'll have to use this to help us along in the problem and to graph it and everything. Now, let's look for intercepts. So let's find the x-intercepts first. All right, so for the x-intercepts, that is where x squared over the square root of x plus 1 equals 0. And we know this is 0 when x squared equals 0. So that tells us x is 0. So our x-intercept is 0, 0. All right. Remember, to find your x-intercepts, you just set the function equal to 0, solve for x. Now we need y-intercepts. So the y-intercept, well, of course, we know what we're going to get. We're going to get 0. We're going to get the point 0, 0, but I'm still going to go through and show you because you're not going to get the same thing every time. So we evaluate the function at 0. So I plug 0 in here for x. All right, and you can see we're going to get 0, 0, and we already knew that. Okay. All right, now let's test for symmetry. So we can determine if it's odd or even. We know it's not a periodic function, but we're going to test to see if it's odd or even. So remember, to do that, we evaluate the function at -x. And what I'm going to do, I'm going to go ahead and write the function down here so we can see it. All right, so we're going to replace the x values with -x. That's going to be -x squared over the square root of -x plus 1, which is x squared over the square root of -x plus 1. Now, we didn't get y of x back. We didn't get -y of x. We got something other than that. So this is not symmetrical. All right. And now we have asymptotes. Let's write that in a different color. All right, so let's look for vertical asymptotes first. So I've got the vertical asymptotes. All right. So for vertical asymptotes, we want to see where is the function, where is it 0. So let me take this and pull it down so we can see it. All right. So we know to find the vertical asymptotes, where's the denominator 0? So where's that denominator 0? At -1. So remember, once again, to show that there's a vertical asymptote, you would have learned this earlier on in your calculus class. So it's undefined at -1, so you can take the limit as x approaches -1 from the left or from the right, or the limit as x approaches -1. If any of those equal plus or minus infinity, then that means there's a vertical asymptote there. And so I'm going to do the limit as x goes to -1. All right, now let's be careful here. All right. Remember, the domain is -1 to infinity. Okay, remember that. So, what we've got here, if you look at this on a number line, there's -1. Our domain is from -1 to positive infinity. I can only take the limit as x approaches -1 from the right. You see that? From the right-hand side. I can't come in from the left because these numbers are not in the domain of the function. All right? So we don't have to take the limit coming in from the left. Now we can't. All right? So, and that's going to be x squared over square root of x plus 1. So if I'm coming in from the right-hand side, you've got to understand that I'm plugging in numbers like -0.9999 and so on. We're getting closer and closer to -1 from the right-hand side. So if I plug this number in for x, that's going to pretty much give me 1 up in the numerator, and that's where it's going to stay, right there around 1. But in the denominator, you see, if I plug in the -0.9999, that's going to give me 0.00001. I think I got that the right amount of zeros. But anyway, the closer we get to -1, this denominator is getting smaller and smaller and smaller. Okay, and the numerator staying at 1, so this thing is going to infinity. So that means we have a vertical asymptote at x equal -1. Now for the horizontal asymptotes, we take the limit as x goes to infinity and the limit as x goes to -infinity. So we're going to take the limit as x goes to infinity of x squared over the square root of x plus 1. Now, also be careful on this one. We can only take the limit as x goes to infinity. We can't take the limit as x goes to -infinity because the numbers over here going to -infinity are not in the domain of the function. So we can only do the limit as x goes to infinity. So this is the limit as x goes to infinity of x squared over the square root of x. You just keep the largest the largest exponent from the numerator and the largest exponent from the denominator. All right, you did this back when you did limits. Okay, this would have been the first chapter you covered in calculus. If you're not sure on what I'm doing here, you just make sure you keep the largest from the numerator, largest from the denominator. I've got a video on this. Just search my channel for finding limits at infinity, and it should come up. And so this is the limit as x goes to infinity, and that's going to be x squared over x to the 1/2, which is the limit as x goes to infinity of x to the 3/2. Subtract exponents when you have like bases, and so this is going to be infinity. So when we took the horizontal asymptote, notice that did not approach any number. It's going to infinity. So the horizontal asymptotes, there's none. All right. All right, so now the fun part. Let's look at this. Now we get to do increasing and decreasing. All right, so let's write the function down again. And we've got to take the derivative of this thing. All right, so we get y prime is equal to, so this is the quotient rule, so it's the derivative of the numerator times the denominator minus the derivative of the denominator. Now, to take the derivative of square root of x plus 1, there's a shortcut when you're finding the derivative of a square root. It's just 2 times whatever the square root is. Okay, we're taking the derivative of square root of x plus 1. So it's 2 times whatever that is. That goes in the denominator every time. And the numerator, well, look underneath the square root. What's the derivative of that? 1. And that's your derivative. And if you need to see more on that, I've got a video. Search my channel. Shortcut for finding derivative of square root. Okay, and then times x squared. And that's all over the square root of x plus 1 squared. All right. Now, what do we do now? Well, now we got to simplify this thing. Well, we can look at this as being fractions like that. And this is just simplifying a complex fraction that you did in algebra. So how are we going to simplify the complex fraction? Well, look at the 1 here, the 2 square root of x plus 1 here, and the 1 here. Common denominator is 2 square root of x plus 1. So we got 2 square root of x plus 1. We're going to multiply that to each term. All right. And so that is going to give us y prime is equal to, that's going to be 4x times x plus 1 minus x squared. And that's going to be over x plus 1 times, and there's going to be a 2 there, and that's going to be times x plus 1 to the 1/2. So I just changed square root of x plus 1 to a 1/2 power. All right. And so that's going to be 4x squared plus 4x minus 4x squared over 2 times x plus 1 to the 3/2. And so that is going to give us y prime is equal to 4x over, no it's not, no I'm sorry, I don't know where the 4 came from. That's just minus x squared. I have no idea where I got the 4 from. That's 3x squared plus 4x over 2 times x plus 1 to the 3/2. You know, where that 4 came from, don't know. I guess I must have been looking at one of those 4s when I was doing that. So, but anyway. All right. 4x squared minus x squared is 3x squared. Not 0. Well, no. Yeah. Anyway, let's go. All right. So now I'm finding my critical numbers. So I've got to set the first derivative equal to 0. Okay. So remember, y prime is equal to 0 when 3x squared plus 4x equals 0, which that gives us x times 3x plus 4 equals 0. And so I get x is equal to 0 or x is equal to negative 4/3. All right. So there's the critical numbers. And once again, be careful here. That I can scratch out. Why? Because remember, my domain is -1 to infinity. Negative 4/3 is not in the domain of the function. So that's not going to be a critical number. Okay, it would give me a negative underneath the square root, and I can't take the square root of a negative number. All right, so now I've got to do my number line. All right, and I'm going to put the 0 on there. Now, remember your critical numbers, that's where the first derivative is 0 or where it's undefined. Okay? Well, it's undefined at -1. The first derivative is. But remember, it also has to be in the domain of the function, of the original function. And -1 is not in the domain of the original function. So -1 is not a critical number. But we're still going to put it on the number line because it could change increasing, decreasing. Okay? So remember, you get your critical numbers, plot those on there, and plot the numbers where the first derivative is undefined. Plot it on the number line. But at the same time, remember in this case that -1 is not a critical number because it's not in the domain of the function, but we're still plotting it on the number line. All right. And so I'm going to choose x equal -1/2 and x equal 1. And that's something that's kind of nice about this problem. We don't have to pick a number over here because the domain is -1 to infinity. All right, that's one reason it's really important at the first of the problem when they tell you find the domain of the function. Okay, you can see the difference it's made on this one. All right, and so now I've got to do f prime of -1/2. So let's see what we get. F prime of -1/2, I believe that is going to give us a negative number. That's going to be less than 0, so that's decreasing. And f prime of 1, now the -1/2, I'm plugging it into the first derivative. Okay, and the f prime of 1, I'm plugging it into the first derivative, and it's actually not f prime, it is y prime. All right. Now, I don't care when I plug these numbers in, I don't care what the exact answer is. All I care about is it positive or negative. And then when I plug the 1 in, I'm going to get a positive number, so that would be increasing. And so I could say this thing is decreasing from -1 to 0, and it is increasing from 0 to infinity. All right, so let's put a box around that because we'll have to use that when we go to graph it. And now I have my local max min. Well, you can see here I have a local minimum at 0. And so I have a local minimum at 0. And then how do I get the y coordinate? I got to take the 0 and plug it back into the original problem. So let me go up here. There's the original problem. Let's just pull this down. All right. And then obviously we know this is going to be 0. Say 0 squared. I mean, we already know that's your x and y-intercept. 0 plus 1 is 0. Students mess up on that all the time when they're finding their local max and min. I've seen a lot of times students will take this 0 here and plug it back into the derivative for some reason. You don't do that. I mean, in this case, you would get lucky because it would give you 0 as an answer, but that's not going to happen all the time. Okay, so you've got to be careful about that. Remember, when you're looking for a point, you take the x coordinate and you got to plug it back into the original function to get your y coordinate. All right, so there's your local minimum. All right, so now we got to test for concavity. So for concavity, I need the second derivative. So let's look for concavity. And I'm going to go ahead and let's write the first derivative down. That's 3x squared plus 4x over 2 times x plus 1 to the 3/2. And you know, the problems that we're working in this video, I mean, these are the difficult ones. And what makes them so difficult is just finding the derivatives, because these derivatives get so nasty trying to find them. All right, so let's find the second derivative. All right, so once again here we have what? We've got quotient rule. So the derivative of the numerator, that's going to be 6x plus 4. That's the derivative of the numerator, times the denominator, 2 times x plus 1 to the 3/2. All right, minus the derivative of the denominator, so the 3/2 times 3, I got to do chain rule here, 3/2 times 3 is 3, times x plus 1 to the 1/2, subtract 1 from the exponent, times the derivative of what's inside the parentheses, so the derivative of x plus 1 is 1, times the numerator, 3x squared plus 4x. And this is all over the denominator squared. All right. All right. So now comes the fun part. We get to simplify this thing. So if you notice here, I've got a common factor of x plus 1 to the 1/2. I'm going to factor that out. And by doing that, it's going to make this a lot easier to simplify. So I've got y double prime is equal to, so I'm going to factor out an x plus 1 to the 1/2. And that is going to leave me 6x, well, let's do this, 2 times 6x plus 4 times x plus 1. All right, so when I factor out x plus 1 to the 1/2, see, this is like one big term right here, and I'm factoring this out. So what am I left with right here? Well, what's 3/2 minus 1/2? That's 2 over 2, which is 1. Okay, minus, and then that's going to be 3 times 3x squared plus 4x. All right, you'll see that whole x plus 1 to the 1/2, that whole thing comes out here. All right, and that's going to leave me with 4 times x plus 1 cubed. All right. All right, so let's full this out, and we'll distribute that 3, I guess. So that's going to be y double prime is equal to, so that's going to be 2 times, that's going to be 6x squared plus 6x plus 4x plus 4 minus 9x squared plus 12x over 4 times x plus 1 to the 5/2. All right, so what in the world went on there? Okay, what went on there? Well, let's look at that. I've got like base here and here. So if I bring this down and multiply, I subtract the exponents. So what I did there is that's x plus 1 to the 3 minus 1/2. See, I brought it down here, and 3 minus 1/2, that's where the 5/2 comes from. All right, so let's see what we got. So I've got y double prime is equal to, all right, so let's do a few things. Let's do a few things right here, I guess. So that's going to be 12x squared, and then I'm distributing the 2, so 12x squared. 6x plus 4x is 10x times 2 is 20x plus 8 minus 9x squared plus 12x over 4 times x plus 1 to the 5/2. And I'm sure hoping I didn't make any kind of stupid arithmetic mistake. So that's 3x squared. Hang on. And I did make a stupid arithmetic mistake, didn't I? The negative, I don't know why I put a positive there. That's minus. Whoop. And that's minus. All right, so let's see, we've got, what is that? That's going to be plus 8x plus 8 over 4 times x plus 1 to the 5/2. All right, so let's see what we've got here. Now, remember, y double prime is equal to 0 when 3x squared plus 8x plus 8 equals 0. Now, I'm not going to go through and do all this work because you can do this. X is equal to negative 8 plus or minus the square root of 8 squared minus 4 times a times c all over 2 times a. And when you do this, you're going to get a negative under the square root. So you got 64 minus 12 times 8, which is negative 32. That's an imaginary solution, so this is never going to be 0. So remember we're testing for concavity. So what happens now is, well, not because it doesn't equal 0, but just like what we did with the increasing decreasing, we want to also use where the denominator is equal to 0. Okay, now remember these values, when you take the second derivative, you set it equal to 0 and you solve for x. These values that you use, that's where there's a possibility of an inflection point. But keep in mind on this negative 1, we are going to plot it on the number line to determine concavity. All right, we are going to plot it on the number line, but remember, there's no possibility of an inflection point being at negative 1 because the function, the original function, is undefined at negative 1. And there's also another reason, and I'll explain that in a minute. So let's go ahead and pick our point. We'll just choose x equals 0. And so if we do y double prime of 0, well, if we plug the 0 in here up top, that's positive. Down here's positive, so that's greater than 0, so it's concave up. And so we would say this thing is concave up from negative 1 to infinity. So we need to use that. Now you might be thinking, well, why did you just do on the right hand side of negative 1? Do you know the answer to it? Remember, the domain is negative 1 to infinity. Remember that. I can't pick anything over here. All right. Once again, that's why it's important to find that domain. And so now we do inflection points. And that would be none, because it doesn't change concavity anywhere, does it? So there's no inflection points. So now all these things that we've circled as we've been going through and working the problem, we've got to use all of that to graph our function. And so what I'm going to do is I'm going to write all that stuff down here so we have it together. Okay, I'm going to go back and write all that stuff down, right down here. I'm going to pause the video while I do it. All right, so I've got all the stuff written here. So now let's graph this thing. So I've got -1 here, and I know I have a vertical asymptote there, right? And there's my point 0, 0, and that's really the only point that I'm going to be plotting on there. So now let's graph it. So as I'm approaching -1 from the right hand side, okay, I've got a vertical asymptote there, so maybe I need to, I guess I should have written that down. As I approach -1 from the right, this right here, it's going to infinity. All right, so I should have wrote that down. But see, as I'm approaching -1 from the right, the graph is going up to infinity. All right, and I know also from -1 to 0, from -1 to 0, this thing is decreasing. It's concave up the entire domain of the function. So I know it's going to look like this. And then from 0 to infinity, it starts increasing again. So I can draw this thing in there. Kind of draw this thing in there like that. There's your graph. All right, so that one wasn't too bad. All right. So let's look at number 3. All right, so let's see what we've got here. We've got f of x is equal to x times e to the x, and we want to graph this. So we want to find, once again, domain, intercepts, symmetry, asymptotes. We want to know where is it increasing, decreasing, local max min, concavity, points of inflection. So let's go ahead and get started. So the first one, the domain, well, that's easy. The domain here, that is going to be -infinity to +infinity, because we can plug anything in for x. There's not a number that's going to make it undefined or break any math rules. So -infinity to +infinity. Now let's look at the intercepts. All right, so let's find the x-intercept first. So remember, to find the x-intercept, that's where you set the function equal to 0 and solve for x. So here we've got x is just equal to 0. This x right here, we set it equal to 0, so x is 0. Now the e to the x, there's no need in setting that equal to 0, because an exponent is never going to be 0. There's nothing we can plug in for x to get 0. All right. And then we've got our y-intercept. Well, first, our x-intercept is 0, 0. And guess what? We're going to get the same thing for the y-intercept. But let's go ahead and show the work. So to find the y-intercept, you're just going to plug 0 in for x. So that's going to be 0 times e to the 0, which is 0. And of course, we're going to get the point 0, 0 again. So let me circle those, because we're going to have to use all this information here to graph. All right, so we've got our intercepts. Now let's look at symmetry. All right, we want to know, is it symmetrical? Is it an even or odd function? Okay, is it symmetrical about the y-axis or the origin, or is it a periodic function? Well, we know it's not a periodic function. It doesn't repeat. That's, the periodic functions like sine and cosine and tangent. Okay. But let's test for symmetry. So remember how to test for symmetry. We're going to take the function and we're going to evaluate it at -x. So let me go ahead right here And let's just go ahead and write the original problem down so we can see it. We'll bring it down as we go so we can see the problem. All right, so this is going to be negative x e to the negative x. Now, when we put negative x in for x, well, we don't get the same function back, do we? No, so it's not an even function. And if we factor out a negative, in other words, this negative, if we look at that as being by itself, and then we look at just this part right here, I don't have negative and then f of x in here, do I? No. So it's not an odd function either. So symmetry, that would be none. All right. All right, so now the asymptotes. That's where we're going to look for the horizontal and vertical asymptotes. All right, so let's go ahead and find the horizontal asymptotes first. So the horizontal asymptotes, remember how to do that. That's where you take the limit of the function as x goes to positive infinity, and we take the limit of the function as x goes to negative infinity. So, you know, the horizontal and vertical asymptotes, that's something you learn towards the beginning of your calculus class, how to find those. Well, we can see here as x goes to infinity, well, this x here is going to infinity, and this e to the x is going to infinity. So we've got a really big number times another really big number. And what's that going to give us? That's going to give us another really big number, right? So that's going to infinity, okay? So based on that tells us there's no horizontal asymptote. But keep in mind, we've only checked as x goes to infinity. Now let's check as x goes to negative infinity. So that's x times e to the x. So for this one, we've got negative infinity, okay, as x goes to negative infinity. This x term goes to negative infinity. But what does this e to the x do? Well, that e to the x, that's e to the negative, raised to a negative number out there at negative infinity, okay? E raised to a really big number with a negative sign in front of it, okay? So actually it's a really small number. So what do we do there? All right. Well, if you look at it, e is going to be raised to a negative number. Well, if we rewrite this thing, well, first let's just look at e to the x. So if I've got just e to the x by itself, then what that does is as this is going to negative infinity, okay, we can look at that as 1 over e to the negative x. If I look at that as a fraction and bring it down. So as x is going to negative infinity, the negative and negative make a positive. So I've got 1 over a really big number, which means this term right here, this e to the x, that would be going to 0. But remember, when you're doing limits, you can't say negative infinity times 0 is 0. I mean, 0 might be our answer, but it's not because of that. All right? So what we need to do is, let's see if we can maybe rewrite this thing. So maybe we get infinity over one of the infinities over infinity, something like that, and we can use L'Hopital's rule. So we've got the limit as x goes to negative infinity, and let's write this as x over e to the negative x. So you can see the numerator is going to negative infinity, the denominator is going to positive infinity, because we got a negative and then a negative is a positive. So I can apply L'Hopital's rule. So that's going to be the limit as x goes to negative infinity of 1 over negative e to the negative x. All right, so now what happens? Well, as x goes to negative infinity, well, that's e to a really big number because the negative and negative make a positive. So this whole fraction here, that would be going to 0. And so that tells us we have a horizontal asymptote at 0. All right. Now for the vertical asymptotes. All right, let's bring this down so we can keep looking at the function as we work the problem. All right, so vertical asymptotes, well, right off the bat, we know that is none, because there's nothing that makes that function undefined. Remember, when you're looking for those vertical asymptotes, what's going to give me a 0 in the denominator? All right, and then we would have to, of course, whatever gives you 0 in the denominator, you got to take the limit as x approaches that number from the left and from the right, and it's got to either go to positive or negative infinity in order for it to be a vertical asymptote. If you need to look at that on how to find vertical asymptotes, well, you can search my channel for vertical asymptotes, and you should, I think I got a video on it, so check that out. All right, so now let's look for increasing and decreasing. All right, so for increasing and decreasing, remember we've got to find what? We've got to find the critical numbers, all right? And then we'll plot those on the number line. So I've got to take the derivative. So I've got f prime of x is equal to, now for this one I'm going to do the product rule. This one isn't that bad, so that's going to be the derivative of the first term times the second term plus the derivative of the second term times the first term. And then I'm going to write this as f prime of x is equal to, and I'm going to factor out an e to the x, and that's going to leave me with 1 plus x. And so now we set that equal to 0, and we solve, so we get x equal -1. And so now remember, the e to the x, there's no need in setting that equal to 0. I just set the 1 plus x equal to 0. But e to the x will never be 0. Okay? So the -1, that's what I'm going to plot on the number line. And that's going to split this up. And I'll pick -2 and 0. You can pick whatever you want, just as long as you pick a number in each region. And so then we have f prime of -2. So I'm going to take the -2 and plug it into my derivative. I'm going to plug it into this one. I could plug it in up here if I wanted to, but this one's just easier. Now remember, no matter what I plug in for the x here, for this e to the x, this e to the x is always going to be positive. It'll never be negative. So I just need to plug the -2 into here. So that's going to give me a negative times a positive is negative. And remember, that's really all you care about. Is it positive or negative? We don't care about what the exact number is. Okay? And so since this was less than 0, that means on this interval, it's decreasing. Now let's do f prime of 0. So that's going to be positive times a positive, which is positive, and so that means it is increasing. And so this thing is decreasing from -infinity to -1 and increasing from -1 to infinity. All right. And now we need local max min. So let's look at that. Max min. And once again, let's bring the function down here. All right. So where's there a max min? Well, that's what's so good about finding the increasing and decreasing. See how it helps you? We got a local minimum right here at -1. All right. So we have a local minimum at -1. All right. And now I need the y coordinate. So we're going to do what? We're going to evaluate the original function at the x value. That's where students mess up all the time. A lot of students will take that -1 and plug it back into the derivative. Okay, that's not right. We're looking for an x-y coordinate. So if you got an x coordinate, how do you find your y coordinate? You plug it into the original. And so that's going to be -1 times e to the -1. And that gives us -0.37. -0.37. So there's our local minimum. All right. All right. Now let's check for concavity. So we got concavity. We'll know where is it concave up, concave down. So we've got to find the second derivative. So let's go ahead and let's write this first derivative down, because we're just going to take the derivative of the first derivative, right, to find the second. So that's e to the x times 1 plus x. All right, so once again, here we have what? We've got the product rule. And so I have f double prime of x is equal to, okay, e to the x is, I'm going to make that my first function, 1 plus x, that's my second function. So remember, it's the derivative of the first function times the second function plus the derivative of the second function times the first function. So the derivative of the first function is just e to the x times the second function plus the derivative of the second function times the first function. And then, of course, we're going to need to simplify this sum. So that's going to give me f double prime of x. And I'm going to do what? I'm going to factor out e to the x. And that's going to leave me with 1 plus x plus 1. So I get f double prime of x is equal to e to the x times x plus 2. All right. And so we're going to take the e to the x times x plus 2. You set the second derivative equal to 0, and once again we get x is -2, and you do not set the e to the x equal to 0 because it's never going to equal 0. Okay, so we're going to do a number line. We're going to plot the -2 there, and that breaks it up into two regions. So I'm going to pick x equal -3, x equal maybe -1. How about that? And so now we're going to evaluate the second derivative at each of these values, and all we care about is it positive or negative. Remember, if it's positive, it's concave up. If it's negative, it's concave down. We don't care what the exact value is. So once again, the e to the x, no matter what number I plug in for x, that e to the x is always going to be positive. So when I plug the -3 in, that's a negative times a positive. That's less than 0. So this is concave down. And when I do f double prime of -1, that's going to be a positive times a positive, which is positive. And so that's concave up. So we got concave down from -infinity to -2, and concave up from -2 to infinity. All right, so we got to use all this stuff to sketch our graph. Now we're looking for inflection points. So where are the inflection points? Well, the inflection points, that's where it changes concavity. Well, where does it change concavity? At -2. It changes from concave down to concave up. So we've got inflection points. All right. And let's bring the original function down. So we can see this. So we've got an inflection point at -2. Okay, that's where it changed concavity, right here at -2. So once again, we got to get our y coordinate. So we plug the -2 back into the original function. So we've got f of -2 is -2 times e to the -2, which that is -0.27. -0.27. And there's our inflection point. So now we've got to go and use all that stuff that we found, okay, all that stuff we found, and use that to sketch our graph. So I'm going to write all that stuff down here. I'm going to pause the video while I do it. All right, so we've got all the stuff written down, okay. So now let's draw the graph. All right. Let's do. All right, each one of the marks is, we'll consider that 1 unit. So let's plot the point 0, 0. Then let's plot our minimum, our local minimum, -1, -0.37, which we'll say that's about right in there. And then let's plot -2, -2.7, which we'll say is about right in there. And so that's all of our points. All right, so let's look and see what this thing's doing. So it's decreasing until we get to -1. So that means it's decreasing and then it starts increasing. At x equal -1, it starts increasing. And it's increasing from -1 to infinity. So on the left-hand side of -1, it's decreasing. On the right-hand side of -1, it's increasing. All right, so now let's look at concavity. So it says here it's concave down from -infinity to -2. So when it's coming in from this side, it's concave down. And once it gets here, it changes to concave up. Now, when it comes in, is it going to come in from up here? Okay, is it going to come in from up here like this? What's it going to do? Well, let's see. It says as x goes to -infinity, see this limit? That goes to 0. The function goes to 0 as we go to -infinity. So it's not going to go up like that. And also, you know, we do have a horizontal asymptote here at y equals 0, which is just the x-axis. So what this is going to do is going to get closer and closer to this x-axis as it's going to -infinity. And it's going to come in here like this. It's concave. Remember, it's concave down. But once it hits the -2 and goes to the right of -2, it changes to concave up. So it's going to kind of look something like this. All right, see, it's concave down, then it changes to concave up, and then it's going to come in here like this. And see, it's concave up the rest of the way from -2 to +infinity. And that would be your graph. All right. Whoop, I'm sorry. Let's see. I actually need to redraw that. It's kind of hard drawing this one in there. There we go. I think that looks a little better. All right. See, it does change to concave. And I guess I kind of exaggerated it there. But also keep in mind this right here. It's hard drawing this one in there. It's going to come in here like this. there, that's better. Because this right here, this point right here, that is a local minimum. So, and I think at first I had it drawn kind of a little bit down here, you know, in this part, but you get the idea. Draw it in the best you can. You know, I think, you know, as far as I go, yeah, you know, you want to draw it accurately, but you know, if you get your points right, and you know, you come over here and you can label your points and stuff, you know, that's showing you know what you're doing. So, you know, that's that one. It wasn't too bad. So let's look at the next example. All right, so let's take a look at this problem here. We got f of x is equal to cosine x over 2 plus sine x, and we want to graph it. So we need to find once again, the domain, intercepts, symmetry, asymptotes, increasing, decreasing, local max, min, concavity, and points of inflection. All right, so first thing, let's find the domain. All right, so obviously here the domain is negative infinity to positive infinity. We can plug any numbers we want in for x with the trig functions. Well, for not all trig functions, but sine and cosine we can. So that's negative infinity to positive infinity. Now it would be different if it was secant or cosecant or cotangent. But for sine and cosine, we can plug anything in. Now, let's look at the intercepts. So we want to find the x and y intercepts. So let's find the x-intercept first. So we're going to take cosine x over 2 plus sine x, set it equal to 0. So remember, this is 0. This equals 0 when the numerator's 0. All right, so when is cosine 0? And look, if you need to, just sketch the graph of cosine. There's pi over 2. There's 3 pi over 2. See that? So when x is equal to pi over 2, 3 pi over 2, and then if we kept going, that would be what? 5 pi over 2, and then what? 7 pi over 2, and so on. All right? So there's an infinite number of x-intercepts. It goes on forever. So what we would have is, if we wrote this, that would be pi over 2 plus n times pi, where n is an integer. So there's all your x-intercepts. And look, I'll go ahead and tell you right now, and I'll talk about it more when we get down to that part. I mean, you remember that the trig functions, those are periodic functions. They repeat, okay? So really what I'm going to do while I'm getting all my information, yeah, I listed all the x-intercepts, but at the same time, I'm going to kind of focus on that 0 to 2 pi, the period of the function, okay? And then once you get that drawn, then you can just fill out all the other intervals. You'll see more what I'm talking about as we work through the problem. Now, let's find the y-intercept. So remember, the y-intercept, that's where we just evaluate the function at 0. So that would be cosine of 0 over 2 plus cosine 0, which that's going to be what? That's 1, and then 2 plus, I'm sorry, that's not cosine. That is sine. 2 plus 0, which is 1/2. So the y-intercept is 0, 1/2. All right. Now, let's look for symmetry. All right. So remember, symmetry, that's where we evaluate the function at negative x. So we're going to find f of negative x, and that's equal to cosine of negative x over 2 plus sine of negative x, which that's going to be cosine x 2 minus sine x. All right, so remember, we plug the f of negative x in. Did we get f of x back, the original function? Let's just write the original function here so we can see it. All right, so you can see we didn't get the original function back, so that means it's not even. Now, am I going to get the negative and then the original function? So, in other words, I could factor a -1 out of the denominator, and if I do that, I get what? I get -2 plus sine x, right? Well, if I move this negative up here, did I get negative f of x? Well, no, this is not f of x here. So that means it's not odd. So this one is neither. It's neither odd nor even. All right. Now, on to the asymptotes. All right, so let's look at vertical asymptotes. All right, so the vertical asymptotes, so remember to find those. Well, where is the function undefined? And then we've got to take, wherever the function's undefined, we've got to take the limit as x approaches that number from the left and from the right, and it's got to approach infinity or negative infinity in order for there to be a vertical asymptote there. But as you can see here, this denominator will never be 0 because sine x will never be -2. Remember, the range on sine is -1 to 1. It's always going to, whenever you take the sine of an angle, it's always going to be between -1 and 1. So it'll never be -2. So for vertical asymptotes, there's none. And then horizontal asymptotes, well, that's going to be none also. We take the limit as x goes to infinity and negative infinity. And what does sine and cosine do? It just oscillates back and forth. Okay? So for vertical and horizontal asymptotes, there's none. But this is a periodic function. It is a periodic function because we have f of x plus 2 pi is equal to f of x. Remember, the sine and the period of sine and cosine is 2 pi. So we do know it's a periodic function. It's going to repeat. Okay? It's going to repeat every 2 pi. All right, so we got that out of the way. Now let's look at the increasing and decreasing, and let's see what that does. All right, so we've got increasing, decreasing, all right, so let's write our function down, because remember, we got to take the derivative. All right, so let's take the derivative. So this is quotient rule, so I get f prime of x is equal to the derivative of the numerator, which is negative sine x times the denominator, minus the derivative of the denominator, which is cosine x times the numerator. And this is all over the denominator squared. All right, so now we're going to have to do a little simplifying. All right, let's see what happens here. So that's going to be -2 sine x minus sine squared x, I'm just distributing that negative sine x, minus cosine squared x over 2 plus sine x squared. And so now what I'm going to do, I'm going to factor a negative out of the numerator, so I get f prime of x is equal to negative, and that's going to be 2 sine x plus sine squared x plus cosine squared x over 2 plus sine x squared. And so, well, this is turning out to be not so bad. So this is going to be 2 sine x plus 1 over 2 plus sine x squared. Remember, sine squared plus cosine squared is 1. And so, yeah, there's your derivative. All right, so now we've got to set this equal to 0. But remember, a fraction is 0 when the numerator is 0. So we get sine x equals negative 1/2. Now, hopefully you remember your trig, all right? Solving those trig equations. So we need to get the reference angle. Remember, the reference angle is equal to a positive number, so I've got sine of x prime is equal to positive 1/2. So x prime is pi over 6, or 30 degrees, or pi over 6. Well, I got to figure out what x is. Well, remember, sine is equal to a negative, but I had to change it to a positive so I could get my reference angle, but sine's equal to a negative. Where is sine negative? In the third quadrant. So there's x. So I get 7 pi over 6. And then sine is negative in the fourth quadrant. And that's 11 pi over 6. So I get this is 7 pi over 6 and 11 pi over 6. And yeah, I mean, you can list the other ones, but this is where I get to the point where, okay, I'm going to concentrate on everything between 0 and 2 pi so I can get that graph drawn over one period, and then it just repeats. Okay? All right, so there's my critical numbers. And I don't know why I circled it, because that's not an answer. Well, it is one of the things we're using, but we want to know where is it increasing and decreasing. All right. So when we look at this, the critical numbers, that's where the first derivative is equal to 0, but don't forget it's also where the first derivative is undefined, and in this case the first derivative is not undefined, so we don't have to worry about that. All right, and then we want to plot the 7 pi over 6 and the 11 pi over 6. All right, and so now we pick some values. We pick values in these intervals. So I'm going to choose, I don't know, I'm going to choose maybe x equal pi, x equal, what about 3 pi over 2? Would that work? Yeah, 3 pi over 2 will work. And then I can choose x equal, let's do 2 pi. And so remember, what I have to do now is I've got to do f prime of pi, and you got to take the pi and plug it into here. Now you can, I mean, this isn't really that bad. You could do this, you know, because you should know the sine of pi. The sine of pi would be what? 0. And so that would give us what? Negative 1/2. And so that would be less than 0. So it's decreasing. And then we've got 3 pi over 2. So f prime of 3 pi over 2. Well, if you plug that in, that would be positive. So that's increasing. And then f prime of 2 pi. I guess we could do 2 pi or something in between 11 pi over 6 and 2 pi, but 2 pi will work. That's less than 0, and so that would be decreasing. All right, so this thing is decreasing from what? Now, keep in mind the period of this function is 0 to 2 pi. That's one period, 0 to 2 pi. So I want to cut it off here at 0, and I want to cut it off here at 2 pi. So, I mean, the 2 pi did work in this case. I might should have picked a number in between the two. You know, just keep that in mind. You know, you could pick whatever you wanted to between 11 pi over 6 and 2 pi. But it'll give you a negative number. All right, so it's decreasing from 0 to 7 pi over 6 and from 11 pi over 6 to 2 pi, and then it is increasing from 7 pi over 6 to 11 pi over 6. All right, so we got where it's increasing and decreasing. All right, so we've got that. Now we want to look for local max and min. So we have a local min, there's our local max. All right, so you can see here we have a local minimum here, we have a local maximum here. So we got a local minimum at 7 pi over 6. So that's 7 pi over 6. Whoop. Need the y coordinate. All right, so let's write our function down so we can see what we're plugging it into. So remember, to find your y coordinate, you take the 7 pi over 6 and you plug it into the original function. Remember, you're looking for the y coordinate. So if you've got the x coordinate and you need the y coordinate, you plug it back into the original. So that's cosine 7 pi over 6 over 2 plus sine of 7 pi over 6. And that's going to give you negative square root of 3 over 2. No, negative square root of 3 over 3. All right, so that's negative square root of 3 over 3. I'm not going to go over the evaluating the trig functions, okay? I guess what I can do is I can show you maybe the cosine of 7 pi over 6. Let me just show you that one. So if I'm looking for cosine of 7 pi over 6, all right, which quadrant is that in? That's in the third quadrant, right? This is 7 pi over 6. All right, so let's get our reference angle. So that's going to be 7 pi over 6 minus pi, which is pi over 6. That's our reference angle, pi over 6. So what's the cosine of pi over 6, or the cosine of 30? That's what? Square root of 3 over 2, and I'm in the third quadrant, so it's negative. All right, so remember that, and then you would do the same thing with sine. Sine of 7 pi over 6, that is equal to, well, the sine of pi over 6 is 1/2. I'm in the third quadrant, so it's negative. And then you would just have to do the algebra, the arithmetic there. All right, that's all I'm going to show on that. It'll make the video too long. I mean, it's already a long video, so, but yeah, that's what you got to do. And then we do the same thing here. We have a max at 11 pi over 6. And so we would do f of 11 pi over 6. And that is going to give us square root of 3 over 3. Positive square root of 3 over 3. So there's your local max and min. All right. All right, so now we got to do concavity. All right. So now we got concavity. So for concavity, so let's distribute and clear the parentheses. And I notice here, you see how this and this cancel? All right, that cancels and I'm left with a cubed. So we have f double prime of x is equal to negative, and that's going to be 4 cosine x plus 2 sine x cosine x minus 4 sine x cosine x minus 2 cosine x. And that's 2 plus sine x cubed. All right, so then let's combine like terms. So I have f double prime of x is equal to negative, and that is going to be 2 cosine x minus 2 sine x cosine x over 2 plus sine x cubed. All right, so and we can take it just a step further. So f double prime of x is equal to 2 cosine x times 1 minus sine x. Just factor it out of 2 cosine x. And that's 2 plus sine x cubed. All right, so we having fun yet? All right, so now let's solve this. So remember, a fraction is 0 when the numerator is 0. So that's going to be when 2 cosine x times 1 minus sine x equals 0. So 2 cosine x equals 0, or 1 minus sine x equals 0. And so this is just cosine x equals 0, and this one is sine x equals 1. All right. All right, so let's see, where is cosine 0? So once again, if you need to, don't forget you can always do this. Just sketch it real quick. And you can see cosine is 0 at pi over 2 and 3 pi over 2. And then we want to look at sine. Well, this right here is pi over 2. So this is x equal pi over 2 and 3 pi over 2. Remember, I'm just looking for the ones from 0 to 2 pi, because I'm just going to sketch from 0 to 2 pi, and then you can continue on because it's going to repeat after that. And then this is x is pi over 2. All right. So now let's do our number line. So I've got pi over 2 and I've got 3 pi over 2. And so I'm going to do x equal, how about pi over 4? And remember, I want to stop it at 0 and I want to stop it at 2 pi. And I'm going to do x equal pi. And then how about x equal, I don't know, let's see. How about 5 pi over 3? That's like 300 degrees. That's between 270 and 360. And so I'm not going to go through and show all the work here, but if we took the pi over 4 and we plugged it into here, all right, remember the denominator, this right here will help you. The denominator is going to always be positive because 2 plus sine is only going to be between -1 and 1. So even if a sine is negative, it's not going to be, it's going to be 2 plus -1 at the most. All right. But if we plug this in, we can see this is going to be, let's see, like that's going to be negative. Yeah, it's going to be, and you see what I did? I left off the negative sign in front. See, this whole thing here is positive, but then you got the negative in front, so that's concave down. And then we've got f double prime of pi. And if we evaluated that, that would be greater than 0, so that's concave up. And then f double prime of 5 pi over 3. And you know, you can actually plug these into your calculator to verify them. Just make sure your calculator's in radians. This would be less than 0, so this is concave down. So we've got concave up. Now let's write the concave down first. That's going to be from 0 to pi over 2 and 3 pi over 2 to 2 pi, and then concave up from pi over 2 to 3 pi over 2. So there's your concavity. Now the next thing, inflection points, and I'm going to erase this so we can see that number line there. So inflection points, remember that's where the graph changes concavity. So my inflection points, well, I've got an inflection point at pi over 2. And if you take the pi over 2 and you plug it back into the original, remember the original was f of x is equal to cosine x over 2 plus sine x. So if I plug the pi over 2 in, what am I going to get? Well, the cosine of pi over 2 is 0, so that's going to be 0, and then that's going to come out to be, 0 over 3, which is 0. And then we have an inflection point at 3 pi over 2, and that is also going to give us 0. So there's your inflection points. And guess what? We finally have everything we need to graph this. So let's see what the graph of this thing looks like. So we need all that information we just wrote down, or all that stuff we found. So what I'm going to do is I'm going to come down here and I'm going to write it all down. I'm going to pause the video while I write it down. All right, so I've got all that written there. So now let's draw our XY axis. All right, let's just kind of draw it in right there. And there's 0. Let's call 2 pi over here. Let's leave ourselves some room. So there's pi. There's pi over 2. There's 3 pi over 2. And over here we would have what? Negative pi over 2. And we could extend it on 3 pi. I know that's not the right distance, but you get where we're going. Okay. All I'm going to do is I'm going to sketch in the part from 0 to 2 pi, and that's it. You can extend it either way like you want. All right, so let's see what we've got. Well, we've got our x-intercept, y-intercept. That's at pi over 2, 0, and 3 pi over 2, 0. And let's call this 1 up here, and this is 1/2. So there's 1/2. We got the point 0, 1/2. And then let's see, our inflection. Well, let's Well, there's our inflection points, pi over 2, 0, and 3 pi over 2, 0. But we've got local max and min. So we got 7 pi over 6. So where's 7 pi over 6? Well, that's going to be between pi and 3 pi over 2. And it's probably going to be a little bit closer to here. So we'll just kind of sketch that in, write that in there, 7 pi over 6. And then we've got 11 pi over 6. So that's going to be probably about right in there. All right, and there's your 11 pi over 6. Now for the 7 pi over 6, we get what? Whereas we get negative square root of 3 over 2. So that's going to be, if there's a negative 1/2 right there, it's going to be a little bit past that. And then we've got 11 pi over 6 is square root of 3 over 3. So that's going to be a little bit above 1/2. All right, so it's starting to come in. So now let's look at this. So from 0, let's see, 0 to, let's see, 0 to 7 pi over 6, it's decreasing. So it's going to be decreasing right here. All right. And remember, so it's going to come in something like this. It's going to come in here. It's decreasing. But see, and it changes. And so you see here, it's concave down from 0 to pi over 2. But then it changes to concave up right here. All right. From pi over 2 to 3 pi over 2 is concave up. So it's coming in here like this. And once it gets to 7 pi over 6, where is it? 7 pi over 6 to 11 pi over 6, it starts increasing. So it's going to start doing this. And from 7 pi over 6, let's see, where are we? Let's see, well, no, from pi over 2 to 3 pi over 2, it's concave up. But then once it hits 3 pi over 2 to 2 pi, it's concave down. So it's increasing here. And then once it hits 11 pi over 6, it starts decreasing again. Going to, to 2 pi. And so that's about what it would look like. And then, you would just kind of keep that going in both directions forever. But I would assume if your teacher asked you to graph something like this on the test, they would say, graph it from 0 to 2 pi. But then again, they may not. I don't know. You just, but yeah, that's that problem. That's a pretty tough one there. All right, so let's look at the next example. All right, so let's take a look at problem number 5. All right, so remember, domain, intercepts, symmetry, asymptotes, and then we do increasing, decreasing, max, min, concavity, and inflection points, and then we sketch the graph. All right, so first thing, let's find the domain. All right, so what do we know about logarithms? Well, we know we can't take the log of 0 or a negative number. So that means that 4 minus x squared has to be positive. So we know 4 minus x squared has to be positive, which means it has to be larger than 0. So do we know how to solve a quadratic inequality? So first we want to set this equal to 0 and solve it. So I'm going to get x squared is equal to 4. So x is equal to plus or minus 2. And then we can draw a number line and plot those points there. And then we choose points from each region. And I do have a video on solving quadratic inequalities and rational inequalities. If you want to look at those, you can search my channel. Alright, so what do? We take the negative 3 and we plug it into the 4 minus x squared. Well, if I plug negative 3 into here, that's going to give me a negative, so that would be negative. If I plug the 0 into here, that would give me a positive. And if I plug the 3 in for x, that would give me a negative. So what do we want to know? We want to know, when is 4 minus x squared positive, which is right here. So our domain is negative 2 to 2. All right, so we'll circle that because that's some information we may need. All right, so there's our domain. Now let's look at intercepts. So first, let's find our x-intercept. So remember, our x-intercept, that is where the function is equal to 0. Well, that's where we set the function equal to 0 and solve for x, right? So we're going to take the natural log of 4 minus x squared and set it equal to 0. So the natural log of 4 minus x squared is equal to 0. So now we solve this log. So remember, natural log, that's log base e. So we'll convert this to exponential form. And so I get 1 equals 4 minus x squared. Negative x squared is negative 3. So x squared is equal to 3. So x is equal to plus or minus square root of 3. Now, make sure, the plus or minus 3, it is in the domain of the function. It's between negative 2 and 2. So here's our x-intercept. Plus or minus square root of 3, 0. That's our x-intercept. Now let's look for our y-intercept. Well, remember, the y-intercept is where we just evaluate the function at 0. And so that is equal to natural log 4. So our y-intercept is 0 natural log 4. All right. So we've done domain, we've gotten domain, we've got intercepts. Now let's check for symmetry. All right, so symmetry, remember, that's where you evaluate the function at negative x. So y of negative x is equal to natural log of 4 minus negative x squared, which is equal to natural log of 4 minus x squared. So when I square that, that becomes positive, minus x squared, which this is equal to y of x. So that means this is an even function. All right, so if you need to check on that, some more videos on that, even and odd functions, just go to my channel, search for even and odd functions, and I got a video on just that goes over all that. All right. Now we've got asymptotes. So we need to check for horizontal and vertical asymptotes. So before we do that, let's just go ahead and let's write the function down again so we can see it. And let's look at let's write the domain down also. All right. So for the vertical asymptotes, all right, so remember, that's where we look to see where the function's undefined and we take the limit as x approaches those numbers. Well, the domain of natural log of 4 minus x squared is between -2 and 2. So what we're going to do is we're going to take the limit as x approaches -2. Now look, it might be easier for you to see if we put it on a number line. Okay, now remember the domain is just in between here. So we're going to take the limit. We're going to take the limit as x approaches -2 from the right. See, we can't come in from the left because the numbers out here are not in the domain. So we're going to come in from the right of natural log 4 minus x squared. And what does that equal? Well, if we're coming into -2 from the right, we're plugging in numbers like negative 1.99999. You see that? And that's getting closer and closer to taking the natural log of 0. You see that? And if you remember, if you look at a natural log function, just the basic natural log function, that's going to look like that. And notice as okay, this is y equals natural log x. And as we get closer and closer to taking the natural log of 0, you can see the function goes to -infinity. Okay, so that might confuse you of well, why are you looking at natural log x? Well, I'm not. I'm looking at this. But as we're getting closer and closer to -2 from the right-hand side, I'm getting closer and closer to taking the natural log of 0. Well, what happens is as this in here is getting closer and closer to 0, well, it's going to -infinity. And then we have to take the limit as x goes to 2, but from the left-hand side of natural log 4 minus x squared. Well, this is the same thing. I'm plugging in numbers like 1.99999. I'm getting closer and closer to taking the natural log of 0. So what happens? Well, just like up here, that's going to -infinity. So I have vertical asymptotes at x equal -2 and x equal +2. All right, so now let's look at horizontal asymptotes. All right, so what do we do there? Well, that's where you take the limit as x goes to infinity and the limit as x goes to -infinity. But as you can see, we're not going to go to infinity and we're not going to go to -infinity. It's not in the domain of the function. So we can see here the horizontal asymptotes, we have none. All right, so what do we have now? Well, now we've got increasing and decreasing. So increasing, decreasing. So, so far this one hasn't been too bad. All right, so for increasing and decreasing, let's write the function down again. Y equals natural log of 4 minus x squared. And we have to take the derivative. So y prime is equal to, well, remember how to take the derivative of natural log. Whatever you're taking the natural log of, that goes in the denominator, and the derivative of that goes into the numerator. All right. So y prime is equal to 0 when -2x is equal to 0, which means x is 0. All right. So, because remember, a fraction is 0 when the numerator is 0. So let's do our number line. We've got 0 here, but we also need to plot in -2 and 2, right? That's the endpoints on our domain. So that's going to break up into two regions here. Now remember, I need to draw this dotted line here and here because I can't choose a number out here or out here because those numbers are not in the domain of the function. That's why it's so important at the first of the problem you get the domain, because it makes a big difference. Okay, so now let's choose some numbers. So x equal -1, x equal +1. All right. And another reason we're choosing the -2 and 2 also is if you look at the derivative, you want to choose where the first derivative is 0, and you want to choose where it's undefined. Well, it's undefined at plus or minus 2. See, when 4 minus x squared equals 0, which means x is plus or minus 2. It's undefined there, but keep in mind, 0 is a critical number, but plus or minus 2 is not a critical number because they're not in the domain of the function. All right. So now we've got to test this. So y prime of -1. So if we plug the -1 into here, that's going to be a positive up here, a positive down here. So that's positive. So that's increasing. And then if we do the y prime of 1, well, that's going to be, plug the 1 in here, that's going to be negative, positive, so that's negative. So that's decreasing. So this thing is decreasing from 0 to 2 and increasing from -2 to 0. So there's your increasing and decreasing. All right, so now what do we look at? Now we look at max min. Let me change the color. We got max min. All right, well, look at this. We got a maximum right here, don't we? You see that? It goes from increasing to decreasing, so that's our local max. So we have a max at 0, and then remember, and let's write the problem down. All right, so remember to get your y value. That's just y of 0, which is natural log of 4. So that's natural log 4. And, you know, if you wanted to, you could punch that in your calculator. It's approximately 1.4. It may, you know, going ahead and putting that in as a decimal and at least getting the decimal value out here, that'll help you kind of know where to plot your point. Okay. All right, so there's our local maximum. Now what do we have? Well, now we've got concavity. We know where it's concave up, concave down. All right, so concavity. And so for that, we've got to find the second derivative. So let's first just let's go ahead and write the first derivative down. All right, so now let's take the second derivative. So quotient rule. So the derivative of the numerator times the denominator minus the derivative of the denominator, which is -2, times the numerator. And this is all over the denominator squared. And so I'm going to get y double prime is equal to -8 plus 2x squared minus 4x squared over 4 minus x squared squared. And so y double prime is equal to -2x squared minus 8 over 4 minus x squared squared. And so y double prime is equal to, I'm going to factor a negative out of the numerator. So that's 2x squared plus 8. Yeah, I could have factored out a -2, but I didn't. So that's 4 minus x squared squared. All right. So what do we have here? Well, remember that's where the second derivative is 0. We set that equal to 0, but hopefully you can see that this second derivative will never be 0, because we've got a squared term here. This term's always positive, and you're adding 8, so you'll never get to 0. Okay, and hopefully you can see that this part of the problem right here is always positive. It'll never be negative, this part of the problem. So this is always positive. So that means the second derivative is always negative. Okay, so that means we know it's concave down over the entire domain. And let's just say you didn't recognize that. So remember, to get your points on the number line where you want to see if it's concave up, concave down, it's where the second derivative is 0, and then it's also, you want to see where it's undefined. Well, 4 minus x squared equals 0, so we know x is plus or minus 2. So if you do plot that on the number line, and let's just choose x equals 0. Remember, we can't choose anything out here or out here because it's not in the domain of the function. So if we plug 0 into here, that's going to be positive, that's going to be positive, and then the negative out here, that's negative, so that's concave down. So we know this is concave down from -2 to 2. All right, so we'll have to use that. And then we have inflection points. Well, what about the inflection points? Remember, inflection points, that's where it changes concavity. So does it change concavity anywhere? No. So that would be none. All right. All right, so now we're ready to sketch the graph. So what I'm going to do is all that information that I circled that we found, I'm going to write it down here at the bottom, okay? And then so we can look at it all at once, and I'm going to pause the video while I do that. Okay, so I've got all the stuff written down. So now let's graph this thing. All right. So let's say we've got 1, 2, -1, -2. I've got vertical asymptotes at -2 and 2. All right, so I've got a y-intercept at 0, natural log 4. And remember, natural log 4 was what it was like, about 1.4. So let's see, there's 1, 2, -1, -2. So that's going to be about right in there. And that's our local max. And then we have, well, it's our local max and it's our y-intercept. And then I have x-intercept at plus or minus square root of 3. Well, square root of 3 is about 1.7. So that's going to be about right here and about right here. It'll look something like that. All right, so let's see what else is going on. So I know as x goes to -2 from the left and as x goes to 2 from the right. See here, remember that was -infinity, so we know it's going down like this. And we know on this interval here it's concave down. And we also know that from -2 to 0 it's increasing, and from 0 to 2 it starts decreasing. So we can draw this one in pretty easy. It's going to look, and I know that's not the best drawing, but it's going to look something like that. All right. All right, so let's look at the next example. So this is number 6. I've got f of x is equal to x cubed over x squared plus 1. All right. So let's find the domain. So the domain, that is negative infinity to positive infinity. I mean, nothing makes the denominator 0. It's x squared plus 1. So we know it's all the real numbers. Now, let's look at intercepts. All right, so let's find our x-intercept first. And that is when f of x is equal to 0. Well, that means x cubed equals 0, which means x is 0. And so our x-intercept is 0, 0. And of course, we know that's our y-intercept also, but I'm still going to write it down so you can see it. So the y-intercept is f of 0, which is 0 cubed over 0 squared plus 1, which is 0. And so, of course, there it is. We knew that already. All right, now let's look at symmetry. So for symmetry, now let's go ahead and let's write the function down so we can see it. X cubed over x squared plus 1. All right, so for symmetry, I'm going to evaluate this function at negative x. So I've got f of negative x is equal to negative x cubed. I'm just replacing x with negative x. And so that's going to be negative x cubed over x squared plus 1. And then I'm going to take this minus and I'm going to pull it out to the outside of the fraction. And you can see this is equal to a negative, and then this is f of x. So I know this is an odd function. All right. All right, now let's look for vertical and horizontal asymptotes. Okay, and well, this one's a little special here. So let's look for asymptotes. All right, and let me grab this function and pull it down here so we can see it. All right, so for vertical asymptotes, well, right off the bat, that's none. It's not undefined anywhere, okay? There's nothing that's going to make the denominator 0. Now for horizontal asymptotes, well, there's none there also, but let's work through it and I'll show you why. So the limit as x goes to negative infinity. Remember, we take the limit as x goes to infinity and x goes to negative infinity of x cubed over x squared plus 1. So that's the limit as x goes to negative infinity of x cubed over x squared. Remember, keep the largest exponent from the numerator and denominator. I've got a video finding limits at infinity. Look at that. I go into a lot more detail. And then we got the limit as x goes to negative infinity of x, which that's negative infinity. So we can see there's not a horizontal asymptote as we go to negative infinity. And this one's going to work out the same. The limit as x goes to infinity, x cubed over x squared plus 1. That's equal to the limit as x goes to infinity of x cubed over x squared, which is the limit as x goes to infinity of x, which is positive infinity. So this is none also. All right. Now, this problem has a slant asymptote. When the degree of the numerator is 1 more than the degree of the denominator. Okay? So what we have to do here is we have to use long division. So do you remember how to do long division? All right. So this is going to be, it's going to be x squared plus 1 and then the x cubed in here. But remember, to do that, you've got to do x squared plus 0 times x plus 1 over x cubed, right, plus 0 times x squared plus 0 times x. Okay, we've got to add those in there. It keeps everything lined up. Okay, it keeps everything lined up pretty good. So x times x squared is x cubed, so that's x right there. Then I multiply, so that's x cubed plus 0 times x squared plus x. Change the sign and add, so that's going to be -1. And so I get x cubed over x squared plus 1 is equal to x minus 1 over x squared plus 1. Remember, it's the quotient plus the remainder over the divisor. And so plus the minus and plus, that makes a minus there. So we're going to have a slant asymptote. Let me write that. Well, so a slant or oblique asymptote at y equal x. All right. Now, what's going to happen is, what is this graph going to do? Or how are we going to draw it at that asymptote? Well, as x goes to infinity, okay, as x goes to infinity, do you see how this term right here, okay, this term right here goes to 0 because the denominator is just getting larger and larger and larger. And so this fraction here is going to 0. So as we go to infinity, the function is going to get closer and closer to that line y equal x. Okay, and I'll say that again once we get to the to graphing it. Okay, but yeah, this one you have a slant asymptote when the degree of the numerator is 1 more than the degree of the denominator. All right, so now we have increasing, decreasing. All right, so we need the first derivative, so let's write the function down. F of x is x cubed over x squared plus 1. So the first derivative, that is the quotient rule, so derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And that's all over the denominator squared. And so I get f prime of x is equal to 3x to the 4th plus 3x squared minus 2x to the 4th over x squared plus 1 squared. And so f prime of x is equal to x to the 4th plus 3x squared over x squared plus 1 squared. And I can actually factor out an x squared, so x squared times x squared plus 3 over x squared plus 1 squared. So why did I factor out the x squared? Well, I mean, I really didn't have to, but it makes it easier when you simplify these derivatives as much as possible, because, you know, like right now, what do we have to do? We have to set this thing equal to 0 and solve for x, don't we? So when it's all factored out, it just makes it nicer, okay? So I know here f prime of x is equal to 0 when x squared equals 0, which means x equals 0. All right. Now notice the x squared plus 3, I didn't set that equal to 0 because it's never going to be 0. The only thing that's going to be 0 is that x squared. All right. All right, so that's where it comes in handy to just go ahead and factor it out. All right, so now, and honestly, you know, we're going to set up our number line. Do we really even need to? Do we really even need to set up the number line? No, because we can see this thing, that's squared. That's a squared plus 3. This is always squared. We can see the whole thing is, it's positive always. It's always positive. So that means this graph is always increasing. But once again, let's suppose you didn't see that. So you put the 0 there. You've got x equal -1, x equal +1. So if I plug the -1 in, positive, positive, increasing. Plug the 1 in, positive, positive, increasing. So this thing is increasing from negative infinity to positive infinity. All right. And so now we have local max, min. And of course you can see it doesn't change increasing, decreasing, or decreasing to increasing. So that's none. All right. All right. Now we have concavity. All right. So let's look at concavity. So for concavity, I need the second derivative. So let's go ahead and write the first derivative down. Now, look, use your head on this. Don't make this more complicated than what it is. Okay? Use your head. Think about it. Here's your derivative, this right here. I don't want to take the derivative of that. When I do the quotient rule and I have to take the derivative of the numerator, I got the chain rule right there. You see that? I factored this so it would be easier to solve when I set it equal to 0. Which one am I going to take the second derivative of? This one. Okay? You see, I don't have to use the product rule. And you know, now that I'm thinking about it, I don't know if I said the chain rule when I set up here. If I did, I meant when you took the derivative of the numerator, you have to use the product rule. For some reason in my head, I'm thinking I said chain rule, but anyway. All right. But up here, you don't have to do the product rule. You see that? This one's easier to take the derivative of than this one. So when we write the first derivative down, we're going to write this one down and take the derivative of that. All right, so I've got f prime is x to the 4th plus 3x squared over x squared plus 1 squared. All right, so I've got the first derivative written down. And hopefully you understand why I wrote that one down instead of the one where the numerator was factored. All right, so now we've got f double prime of x. All right, so here we go. Quotient rule, derivative of the numerator, 4x cubed plus 6x times the denominator, all right, minus the derivative of the denominator, that's chain rule, 2 times x squared plus 1. 2 comes down, subtract 1, then times the derivative of what's inside the parentheses, times the numerator. Times x to the 4th plus 3x squared. And that is all over x squared plus 1 squared, squared. Because it's all over the denominator, squared. All right, so how are we going to go about simplifying this thing? Well, if you're still here, that's amazing. Okay. All right. We've had something similar to this in some of the other problems we've done. We're gonna factor out an x squared plus 1. Okay. So I get f double prime of x, and I'm factoring out that x squared plus 1, and I'm going to be left with 4x cubed plus 6x times x squared plus 1 minus 4x times x to the 4th plus 3x squared. And this is all over x squared plus 1 to the 4th, the 2 times 2. All right, so now we've got f double prime of x, and see here, cancels, that becomes a 3. And I'm going to go ahead and FOIL this out, distribute that. So that is going to leave me with 4x to the 5th plus 4x cubed plus 6x cubed plus 6x minus 4x to the 5th minus 12x cubed over x squared plus 1 cubed. And then combine like terms, I get f double prime of x is equal to negative 2x cubed plus 6x over x squared plus 1 cubed. And I'm going to factor out f double prime of x. I'm going to factor out a negative 2x. So the negative there, 2x, that's going to leave me with x squared minus 3 over x squared plus 1 cubed. So now we want to take the second derivative, set it equal to 0. So f double prime of x is equal to 0 when 2x equals 0 or x squared minus 3 equals 0. So x equals 0 or x equal plus or minus square root of 3. All right, so now plot that on the number line. So I've got 0, negative square root of 3. I've got square root of 3. I'm going to pick a number from each region. X equal negative 2, x equal negative 1, x equal 1, and x equal 2. So now we have f double prime of negative 2, and I'm plugging the negative 2 into here. And so when I plug the negative 2 in, I actually get a positive. Yep. And so that's concave up. And then I'm going to plug in the negative 1. When I plug the negative 1 in, that's less than 0. That's concave down. And then I'm going to plug in the positive 1. That's going to be greater than 0. So that's concave up. And then I'm going to plug in the positive 2. That is less than 0. So that's concave down. So I have concave down from negative square root of 3 to 0 and square root of 3 to infinity. And then I have concave up from negative infinity to negative square root of 3 and 0 to square root of 3. So there's the concavity. And so then I have inflection points. All right, so it changes concavity at negative square root of 3, square root of 3, and 0. All right, so my inflection points, negative square root of 3, And remember, to get our y-coordinate, you have to plug that into the original function. And when you do that, you can punch it in your calculator. That's negative 1.3. So negative 1.3. And then we've got square root of 3. It changes concavity. So f of square root of 3, when you plug that into your function, it's positive 1.3. And then it changes concavity at 0, and f of 0 is just 0. Okay, here's the function. F of x is equal to, what was it, x cubed over x squared plus 1. All right, so there's your inflection points. And guess what? Now we're ready to graph this thing. So we've got to take all that information that we found and use it to graph it. So I'm going to write all that down. I'm going to pause the video while we do it, and then we'll graph it. All right, so now I've got all that written down there. So now let's graph this thing. So let's see how good we can graph this. So first thing, let's see, let's see, there's 1, 1, negative 1, negative 1. So our slant asymptote is about like, it's going to look something like that. There's our slant asymptote. This is the line y equal x. All right. Now let's plot all of our other points. Well, we've got the xy intercept, that's 0, 0, and it's also an inflection point you can see here. Then we want to plot, let's see, negative square root of 3, negative 1.3. Okay, so that's going to be about right in here, something like that. And then we got positive square root of 3, 1.3. So that's going to be something about right in there. Or maybe bring it in a little bit, I guess. Maybe something like that. Okay, just kind of eyeballing where these things go. Now, remember, as x goes to infinity and x goes to negative infinity, the graph is getting closer and closer to this asymptote right here, the line y equal x. Because remember, we had, what was it? I think it was x minus 1 over x squared plus 1. Because as x goes to infinity, this term here is going to 0. So it's getting closer and closer to this number here. I mean, you know, just think about it. I mean, it's getting closer and closer to this line here. You know, you go out and then up, out, up, out, up. Okay, so, you know, at 1, we're going to be, you know, if you plug 1 into here, that's 1 minus 1/2. Okay, but as we get larger and larger, this number's getting smaller and smaller. So it's not, you know, it's getting closer and closer to this line. All right, so we can also see from, let's see, where is it? Well, for one thing, it's increasing the entire time. Okay, it's increasing negative infinity, positive infinity. But from negative infinity to negative square root of 3, which is this right here. Let's put that in, negative square root of 3, and we'll put this in as square root of 3. All right, so from negative infinity to negative square root of 3, this thing is what? Concave down. No, it's not. I thought that looked weird. I just wrote those on there wrong. This is concave down. This one's concave up. Yeah. All right. So anyway. All right. Long video. Anyway. So from negative infinity to negative square root of 3, this thing's concave up. But then once it hits this point, from negative square root of 3 to 0, it changes to concave down. And then from 0 to positive square root of 3, it changes back to concave up. and then back to concave down. So this thing's going to look something like this. Whoop. Let me do that in a different color. So it's coming in here like this. It's concave up, and it's let's see how I can, and then it kind of does like this, concave down, and then it comes back into this point. See, it's concave up again here. It's coming in there like that, and then once it hits here, it's getting closer and closer to that line, and it's going to be concave down. All right, so that's it. That's the video. All right, hope it helped. I know it was a long one, and if anybody's still watching the video right now, I would really be shocked. If you are, leave me a comment and tell me. All right. So hopefully this helped. Check out my other videos. Give me a like, share, and subscribe. And thanks for watching. And I'll see y'all later.